Good afternoon, everybody. So this will be a bit of a whistle-stop tour through our Joule-Thomson cooler developments. So in terms of the cryogenic support required for science missions, it's apparent in recent times the medium and large missions certainly requiring a much more varied and bespoke cryogenic approach than might be required for smaller missions or indeed Earth's observation missions. In particular, very low temperatures are being needed now. So, down to 50 millikelvins for some detectors, and it's driving a need for sub-Kelvin cooling in space. And this is resulting in some very complex cryo-chains with basically cascading cooling technologies of ever-decreasing temperatures. And the architecture of these spacecraft and the instruments which are on them are also quite different. So the detectors are very sensitive, particularly with regards to electromagnetic and mechanical disturbances. And they have quite extended architectures, and so often remote cooling is required. There is also quite a lot of congestion in the detector regions, and so you need some very small cold tips, and there are routing constraints how you can get that cold tip in there. And it's a speciality of our cryocooler developments here at RAL, the Joule-Thomson coolers, and it turns out that they are proving to be very useful in solving some of these issues. And I hope to demonstrate that now today with you by taking you through some of the highlights of our recent developments, and in particular, 4 Kelvin cooler we flew on the Planck mission, a 30 Kelvin cooler which we're developing for the Ariel mission, which you've heard on today, and also a 2K cooler in support of the Athena mission. This is a general overview of the cooler. I've got a picture there. It's obviously quite difficult to make a lot of things out. The basic principle of a JT cooler is to perform an expansion of the working fluid across a restriction, and you get Joule-Thomson cooling in that way. The heat exchangers of the cooler are there to facilitate the thermodynamic cycle and to improve the efficiency. The compressors are the workhorse. They drive the fluid around the loop. And some gas handling is needed as well. So I will go through all of these in the next few slides very quickly. Control electronics are also needed. They're not shown in this picture. This is actually a picture of the Planck cooler while we were assembling it for unit level tests. So it's easier to look at a schematic, and I'll go through all of the parts very quickly to give you an idea of how the coolers work. The architecture actually lends itself to an extended accommodation very nicely, because conceptually physically you can split this into warm units and also into cold units. So the warm units, which I've outlined here, comprising the electronics, the compressors, and the ancillary panel, these can be sited remotely, so up to several meters from the very sensitive instrument detectors. And this does reduce the impact of any low-level mechanical, electrical disturbances which come from these items. And they can also be installed completely separately to the cryogenic payload, which is a great advantage. The cold units have no mechanical and electrical disturbances, and of course they can be installed separately into the cryogenic part of the payload. And we have disconnection boxes to physically split these items. So the compressor assembly, as I say, this is the workhorse. It drives the fluid around the system. It comprises moving coil linear motors, reed valves, which rectify the mass flow. Now, these mechanisms are not lubricated. There is no contact between the moving parts, and we maintain a 10 micron clearance between the piston and the bore of the compressor by this Fletcher bearing suspension system. They are zero maintenance, of course, extremely high reliability, and we have demonstrated 10 to the power of 10 cycles with these mechanisms, which is 20 years operation at 40 hertz. And we arrange them in pairs to reduce the exported vibrations. The ancillary panel is there really for gas handling, purification, and housekeeping functions. The getter is there to maintain gas cleanliness over the lifetime of the cooler, and there are filters to prevent migration of any particles. The cooler control electronics essentially communicate with the spacecraft. They provide command and control. They drive the compressors in a closed position loop, and there is an active vibration control algorithm operating in here, typically up to 600 hertz in the piston axis. So this is the cryogenic part, really, the heat exchangers. Now, you need to cool the working fluid below its inversion temperature for JT cooling to occur. And so we have interfaces for pre-cooling that working fluid on these heat exchangers. We have a preference to operate our coolers subcritical. So we accrete liquid in the reservoir, and the temperature is then determined by the vapor pressure. The tube-in-tube counterflow heat exchangers you see run between each cooling stage, and they're there to use the low pressure gas to return the line and to return cool the high pressure line and improve the efficiency. So here you see them coiled up around a commercial cryocooler, but they can be extended obviously into the final routing. And as an example here, I show the Planck Cryo-chain. So this was one of the most important technological achievements of the mission, requiring cooling down to 0.1 Kelvin. The 4 Kelvin Joule-Thomson cooler was in the middle of the cryo-chain. There was a passive cooling chain of the V-groove radiators getting down to 50 Kelvin, and then a 3-stage active cooling chain, of which the 4K cooler that we provided sat in the middle. And this is how it was integrated onto the spacecraft. You can see that the ancillary panel and compressors are contained in the service vehicle at the bottom there. And it's difficult to see, but the heat exchanger snakes up all of the way through the V-grooves up to the cold part at the top there, the 4K interface. And so that had to be preformed and installed in very early in the integration sequence of the spacecraft. And then the V-groove were closed around that. So this is moving on to the 30 Kelvin JT cooler that we are developing for Ariel. You can see immediately from the shape of the spacecraft that it's very similar to architecture to Planck. You have the V-groove radiators there. So again, we have a passive cooling chain from 300K down to 55K. It's in the same orbit as Planck. I didn't mention it's at the L2 orbit location, which is thermally very, very stable. It is, however, a much simpler active cooling chain. There is just one Joule-Thomson cooler, which we will piggyback onto the passive cooling K. It naturally leads to selection of neon as the working fluid. The accommodation and integration will be extremely similar to Planck. So some very brief design considerations and trade-offs that we're going through for this cooler at the moment. The working fluid considerations, the return line pressure determines the temperature, and 3.5 bar gives us the 32 Kelvin. You can see from the figure on the right there that by increasing the mass flow and by increasing the high pressure, you can rapidly increase the cooling power of the cooler. And this is fine. However, in doing so, increasing the mass flow, it does significantly increase the heat rejected to the pre-cooling stages. And this is, of course, the V-grooves, and it will impact the entire passive cooling performance of the spacecraft. So you have to be careful. Similarly, increasing the pressure rapidly increases the compressor input power and also the number of compression stages required. So we would like to stay to 2 compression stages as we did for Planck. Otherwise, you take a very, very large mass penalty. The requirement is 88 milliwatts at 32 Kelvin. There are a whole pile of solutions that you can do to achieve this, but we've come up with the conditions which are shown below, which is a compromise between the wider system architecture and the cooler itself. And we've optimized the compressor and the heat exchanger for these conditions. This is the current status of this cooler. As I say, for the compressors, we've optimized the design. It's important that you operate the compressors at resonance to maximize the efficiency of the cooler. It's important also that we can use identical mechanisms for each compression stage, because in that way, we can minimize the exported vibrations operating in a head-to-head condition. So the demonstration model cooler is currently under manufacture. What you see here on the right is the linear motor mechanism for the compressors. To give you an idea of that, it weighs about 650 grams, that assembly that you see there. I've shown the ancillary panel in the bottom as well, and this has been manufactured and we're currently installing the sensors. In terms of the heat exchangers for the Ariel cooler, They've been manufactured and the test campaign is actually complete for an open loop bottle test. So what you see here is the system coiled up around a commercial cryo cooler. And it's the first time that we've actually demonstrated this type of heat exchanger working with neon as the fluid. And we've demonstrated that we have met the cooling power requirements at the compressor design point. So on with the whistle-stop tour, and moving down in temperature to a 2 Kelvin cooler, and this is in support of the Athena mission. This is an incredibly complicated cryogenic architecture, and I certainly won't go into it here. Ultimately, the detectors need to be cooled to 50 millikelvin. It is a completely different architecture to Planck and Ariel, so that makes it very interesting. You see the spacecraft up on the right there. It's very large. It's 12-meter focal length. It's a Dewar type arrangement. So a traditional sort of Russian doll architecture with ever decreasing temperatures inside the various radiation shields you see there. It's absolutely bristling with coolers, and you can see the representation there. So there are Stirling coolers, which are pre-cooling 4K JT coolers, pulse tube coolers, pre-cooling 2K JT coolers. Together, they cool a hybrid sub-Kelvin cooler, which comprises a absorption cooler and a demagnetization refrigerator. So as I say, extremely complicated. Now, JAXA are actually baseline to provide the JT coolers for this, but ESA have asked us to develop a 2K cooler as a backup solution. It's very different. A very brief run through some of the design considerations. So the working fluid, first of all, is important. It's unsuitable to use helium-4 for this cooler. It has an extremely low vapor pressure, and actually it transitions to a superfluid at 2.17 K. So instead, we're using helium-3, and on the saturation curve, 200 millibars is equivalent to 2 K, and that allows us to reach those temperatures. If for any kind of reasonable performance, you need pre-cooling both at 15 Kelvin and also higher up at 100 Kelvin. And unlike Ariel, where you can continuously increase the high pressure and the mass flow and get more cooling power, with this cooler, you can see top right graph there, surface plot, that it actually curves over. So you get diminishing returns. So you have to be very careful. Increasing the mass flow can completely overwhelm the capacity of the low temperature pre-coolers. If you also, you need to increase the compressor capacity if you do that. And you have a consideration of the pressure drop down the line, which is extremely important. But nevertheless, we found an operating point, and we have been developing a cooler for that. The demonstration model has been manufactured and tested. It delivered performances that you see there, and it has undergone a successful environmental test campaign. The engineering model is currently in manufacture. We've increased the compressor capacity. It's actually using the same motor that you saw previously for the Ariel. And we intend to reach 20 milliwatts of cooling power at 2K with a 15K pre-cooler. And we've made some other small improvements to the cold tip thermal performance, and in particular, the heat exchanger manufacturing process, which is quite difficult. So a summary, you've seen some of the developments. It's been a very quick tour, and I haven't been able to go into a great deal of the technical detail. These are our sort of coming steps and our future work. As far as the Ariel cooler is concerned, we intend to perform system tests of the heat exchangers with the compressors in closed loop in the first couple of quarters of 2021. That will be full cryogenic performance, mechanical environment, and thermal vacuum tests. The qualification model build for Ariel is due to start around about 2022, and that will be tested with payload engineering model. We will upgrade the demonstration model that you've just seen to a life test model around about 2023, and that will run until launch and, in fact, to beyond. As far as the 2K cooler is concerned, Ariel has the priority, but nevertheless, we expect that the system tests of that cooler with the heat exchanger with the compressors will be at the back end of next year, 2021. And the test campaign will be similar to the Ariel test campaign. So thank you for listening. And I believe the floor is now going to be open for any questions that you may have had.
So thank you, Martin, for an excellent talk there about the coolers. Can I just remind people that we're now open for questions, and to start off, looking somewhat further into the future, what is it you're most excited about?
Well, it would be very nice at RAL if we could actually dive into some sub-Kelvin cooler development. But obviously, the most exciting thing was the adoption of Ariel and the realization that we are going to actually be providing hardware which flies, because of course that's ultimately why we're here and what we live for.
Yeah, and how big of a team do you have working on this technology at RAL?
It's not massive, actually, when you compare to some of the other groups around the world. There are around 10 of us working on this, and we have, as well as these Joule-Thomson cooler developments that you see there, we are also working on Stirling coolers. We're working on a 50 Kelvin Stirling cooler for Earth observation. And we're working, one of the particular exciting developments that we've had recently is a very small scale cooler. And this is only weighing 600 grams, providing active cooling at 80 Kelvin. And it's targeted at small missions, so it should be extremely cheap. I mean, it comes with at least 3 zeros off of the price tag of an Ariel cooler. And it should facilitate science for low-cost missions and piggyback type missions.
Okay, that sounds really interesting. So I have another question for you, and that was about the relative challenges between Planck cooler getting down to 4 Kelvin and Ariel at 30 Kelvin. Which do you think is the more difficult to do?
Well, they're both very similar in the sense that they have 2 stages of compression. The technology is essentially the same. You just have to tweak some of the items, but really it might sound a bit crazy, but Ariel could be harder in some respects because of contamination of the neon, which is a problem for us. And in particular, nitrogen in the neon at the level of parts per billion could clog the cooler, and it's very difficult to purify the gas. But cryogenically, clearly 4 Kelvin is a bit harder than 30 Kelvin.
Yeah. So a different question this time, and it's about, can you link this effort on coolers with other types of technology benefits for the Earth?
Yeah, I mean, certainly we're always looking for an application for the space coolers, terrestrial applications, and there are many. We've been particularly looking at the quantum technologies just recently. Essentially anything that's even terrestrial that requires cooling in remote locations or locations that are difficult to maintain, we can offer a benefit for that, and also anything that needs life. Because of course, we have effectively infinite life with these coolers.
Yeah, okay. And another very different question, which is about who is providing the ADR for Athena?
At the moment, well, it's not completely clear, but at the moment, I expect that will be provided by CEA, the French.
Okay. And what are the next steps for Ariel?
So the next steps, it's just moved into phase B2, and we have all of the instruments system requirement reviews coming up. So we're all beavering away very hard. That will happen in January, February, March of the next year, and then ultimately, following that, we would really like to crack on with building the qualification hardware. But clearly, there's a long way to go, and we have to keep pace with the overall development of the payload and the instruments.
Okay, so thanks again, Martin, for an excellent talk. Thank you.